Welcome to this session on SQL Performance Optimization. We will explore the best practices for optimizing your SQL queries to enhance database performance. Get ready to dive deep into the world of efficient SQL. Let's discuss some of the key challenges in SQL performance. Common challenges include inefficient query patterns, missing or improper indexes, poor database schema design, resource constraints, and unnecessary data retrieval. The business impact of these challenges can be significant. You may experience slow application response times, poor user experience, higher infrastructure costs, system bottlenecks, and scaling limitations. Recognizing these issues is the first step toward creating faster and more efficient databases. To optimize SQL performance, it's crucial to use the right analysis tools. One essential tool is the Explain Analyze command. The Explain command reveals the query execution plan created by the SQL Query Optimizer. Use this to identify sequential scans versus index scans, understand join methods in order, and evaluate execution costs and row estimates. Here are some examples of how to use Explain. Explain select asterisk from customers where last name equals Smith. For a more in-depth analysis with runtime statistics, use Explain Analyze select asterisk from customers join orders on customers, ID equals orders, customer ID. Indexing is a fundamental technique for optimizing SQL queries. Understanding different types of indexes is key. There's the B tree, which is the default index type and is effective for equality and range queries. Hash indexes are optimized for equality comparisons only. Bitmap indexes are efficient for low cardinality columns. Covering indexes include all columns needed by the query. Composite indexes involve multiple columns in a specific order. Here are some indexing best practices. Index columns used in the where clauses. Index foreign key columns. Consider column order in composite indexes. Balance between read and write performance. Avoid over-indexing tables. Regularly monitor index usage statistics. Let's look at some query optimization techniques. Let's consider some before and after examples. Inefficient query. Select asterisk from orders where year of order date equals 2024. Optimized query. Select asterisk from orders where order date is greater than or equal to 2024-01-01 and order date is less than 2025-01-01. Inefficient join. Select C.name, O.order ID from customer C, orders O where C customer ID equals O customer ID. Optimized join. Select C.name, O.order ID from customer C join orders O on C. Customer ID equals O customer ID. Here are some key optimization techniques. Use specific column names instead of select asterisk. Avoid functions on index columns. Prefer explicit join syntax over where joins. Use where before having when possible. Limit results with top or limit when appropriate. Use covering indexes for frequently run queries. Consider partitioning large tables. Let's dive into join optimization techniques. There are several join execution methods including nested loop join, which is best for small tables. There's also hash join, which is best for large-to-large tables. And there's merge join, which needs sorted inputs. Here are some performance factors to consider. If you have small tables, use nested loop join. For medium tables, use hash join, and for large tables, use merge join. Here are some best practices for join order. Join smaller tables first. Use statistics to guide join order. Consider using join hints when necessary. There are various join types and their performance implications. Inner join is usually the fastest and returns only matching rows. Left join returns all rows from the left table and can be slower. Right join returns all rows from the right table and is often avoided. Full join returns all rows when there is a match in either table and is the slowest. Cross join is a Cartesian product, Avoid unless necessary. Here are some performance tips. Index all join columns. Use inner join when possible. Filter data before joining tables. Now let's compare subqueries and common table expressions, also known as CTEs. Here's a subquery example. Select product name. Price from products where price is greater than open parenthesis. Select average of price from products where category equals electronics close parenthesis. Here's an equivalent example using CTE. With average electronics AS open parenthesis, select average of price AS average price from products where category equals electronics close parenthesis. Select product name. Price from products. Average electronics where price is greater than average electronics. Average price. Here's a performance comparison between the two. In terms of readability, subqueries are neutral whereas CTEs are better. In terms of query plan reuse, subqueries are not as good as CTEs. In terms of recursion support, subqueries do not provide support whereas CTEs do. With regards to query optimization, subqueries are better, but in terms of code maintainability, CTEs are much better. Let's explore table partitioning strategies. Table partitioning involves dividing a large table into smaller, more manageable pieces. Imagine a large table of transactions. This table can be partitioned by date, such as quarterly. For example, partitions could be by 2023 Q1, 2023 Q2, and 2023 Q3. A query would only scan relevant partitions, improving performance. This is the query path for January 2023. There are several performance benefits. Partitioning improves query performance via partition pruning. It enables faster index operations on smaller tables. It allows parallel query execution across partitions. It makes efficient data archiving and purging possible. When to use partitioning? Use it for very large tables with more than 100 million rows, for time series data with date-based queries, for data with natural segmentation like by region or category, and when regular maintenance operations are slow. Monitoring and performance tuning are crucial for maintaining an optimized database. There are many key performance metrics to monitor. Query execution time, CPU and memory utilization, disk I/O operations, cache hit ratio, lock contention, index usage statistics, table scan frequency, and connection pool efficiency. To monitor these, you can use a variety of tools. These include a performance dashboard for real-time monitoring of database metrics, a query profiler for detailed analysis of slow-running queries, weight statistics to identify resource bottlenecks, and an index analyzer for suggestions for missing or unused indexes. Here is a quick summary of the key optimization strategies we've discussed. Optimize query patterns and use proper indexing. Analyze execution plans for bottlenecks. Choose appropriate join methods in order. Prefer CTEs over subqueries for complex queries. Consider partitioning for very large tables. And monitor performance metrics regularly. Here are some further learning resources. Database-specific documentation, query optimization guidebooks, performance tuning workshops, database administrator communities, and case studies on query optimization. Always remember that performance optimization is an ongoing process, not a one-time task. Keep monitoring, keep improving, and keep learning. Featured image for SQL Performance Optimization. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.